Today we'll be finishing up our look at Dyson spheres with Matrioshka brains, sun-encompassing supercomputers of almost inconceivable computational power. So far we've seen how these objects, Dyson spheres, also known as Dyson swarms or stellar engines, can be used to make more living area for people, to transmute lighter elements into heavier ones, to move ships and planets in whole solar systems, and even to blow up planets and systematically sterilize every planet in a galaxy. We've also mentioned how none of these purposes needs to be exclusive, and today's example is no different. You don't need to devote all of the sun's power just to computer processing, but the Matrioshka brain partially subverts that. While it certainly permits other functions, its architecture tilts heavily towards neo-exclusivity. The very name itself references the Matrioshka doll, a series of nested dolls, each inside the last, because of the way it recycles power at each subsequent layer. It's geared towards maximizing the efficiency of a computer rather than simply dumping solar power into computers. Most descriptions of Matrioshka brains just describe them as a giant computer without explaining the name, but it wasn't picked out of a hat by Robert Bradbury when he introduced the concept about 8 years back. Giant star-powered computers, or even whole planets converted into computers like the Jupiter brain, are nothing new. They were a fairly common staple of science fiction even back in the 1950s, though the increased miniaturization of computers tended to make them less common. It's just hard to imagine why you'd ever need that much computing power. If you've seen the transhumanism or simulation hypothesis videos on this channel though, you can probably guess at why you might. Storing trillions of uploaded digital human minds, whole brain emulations, or simulating whole universes is one of the reasons why you might build computers like this. And of course a third is that it might be one single immense brain, as the second half of the name implies. Even as huge as such brains are, potentially having processing power in excess of 10 to the 49th hertz, trillions of times faster than our best modern computers, there's still a lot of things that would take even a computer like this eons to make a dent in. Concepts like the Library of Babel, a hypothetical library of the sort you'd expect the infinite monkeys working at typewriters would create, would barely be scratched by such a fast reader over the whole life of the universe. And that's something we'll talk about more at a later date, particularly in the context of how many genuinely unique, as opposed to arbitrarily unique, ideas and even personalities can exist. After all, while we can argue that a book with only a few words changed at random is essentially the same book, and with the human mind is constantly changing a little bit here and there, it is hard to argue that a specific exact pattern of information is genuinely, meaningfully unique, and we may need to extend our notion of uniqueness to represent a potentially rather wide spectrum rather than a single specific pattern. We looked at that notion in terms of consciousness and identity, and I think sometime in the near future we need to spend some more time on such concepts. But I'm digressing, back to the mega computer. Why these are nested layers is to allow you to absorb sunlight and then run calculations at high temperatures, which then gets emitted as waste heat. Then in the next layer we absorb that waste heat and run more calculations and emit your waste heat at a slightly lower temperature, and so on. If you picture a classic solar power computer, you have a panel absorbing sunlight and running calculations, and having cooling fans and heat sinks purging that heat. A simple sun-encompassing computer would simply be this scaled up to wrap around the sun, either as a rigid sphere of statites, ultra-thin objects that can float on sunlight like a sheet of paper over a floor vent, an extension of the solar sail concept, or as a swarm of classic satellites. The Matrioshka brain scales this up vertically too, by adding more layers beyond. At each layer the frequencies of light are being decreased, redshifted to higher states of entropy. It's a bit of a skyscraper approach where the generator, a star, is down in the basement. There's a limit as to how many layers you can have, but it's squeezing the sun for every calculation you can get away with. You convert matter, specifically hydrogen, one of the lowest entropy things in the universe, into calculations, one of the most useful things in the universe, recycling your energy at every step. Of course, no recycling process is perfectly efficient, but you can think of it a lot like water conservation, where you use your bath or dishwater to water your garden. Any good machine tries to do this, get a second or third or fourth stage where your waste and leftovers act as a fuel for another process. Without going into the thermodynamics of heat engines, it's usually easiest to picture one of these devices as a series of nested thin rigid spheres, though that is hardly necessary or ideal. Each successive layer is cooler, and I find it's easiest to think of each layer as 4 times further away than the last, since that makes it half the temperature. Now you can take my word on that if you're not math inclined, but to review that fairly quickly, in space, where the only way to cool objects is through thermal radiation, a roughly spherical object's temperature will always be related to its total surface area and the power it is emitting. This also controls its peak wavelength, which for the Sun for instance, our yellow dwarf, is actually in the green range. Colder objects redshift that peak frequency, hotter objects blue shift. But the fusion that drives suns is not producing green photons or yellow ones or any other visible photon. Down the sun's core where fusion happens, it's all gamma radiation. Those gamma rays get absorbed and re-emitted as simple heat, and the sun radiates that heat the same as a glowing red-hot ball of metal or an incandescent light bulb. Since the power radiated by any object, per unit of surface area, rises with the fourth power of temperature, if you double its temperature, it will emit 16 times the power, and if you half it, 1/16. The sun emits at a frequency of light we see because that's the frequency an object with that much surface area can emit that much power without getting any hotter. So to radiate the same power, but at half the temperature, our second sphere would need to be 4 times wider, since a sphere's area goes with the square of its width, 4 times wider, 16 times the surface area, and therefore half the temperature. Now I also like using these half temperature steps because it plugs in easily to Carnot's theorem, that no engine operating between 2 heat reservoirs can be more efficient than a Carnot engine operating between the same reservoirs, and that the efficiency of a Carnot engine is 1 minus the temperature of the cold reservoir divided by the hot reservoir. In this case, the reservoirs would be 2 adjoining layers of Matrioshka Brain, and since each layer is half the temperature of the last, each step is 50% efficient. So if we had our first layer at 1000 Kelvin and our next layer at 500 Kelvin, one a bit closer to the sun than the planet of Mercury and one a bit further away, we'd get an efficiency of 1 minus 500 divided by 1000, or 1 minus 1/2, or 1/2, or 50% efficiency. You might be wondering why we couldn't just jam another layer between those two, and let's say we did. At what would boost 750 Kelvin, about where Mercury would be. Well, that first pair would have an efficiency of 1 minus 750 over 1000, or 1 minus 0.75 or 25%. Not very efficient at all. And the next layer would be 1 minus 500 over 750, 1 minus 2/3 or 1/3 or about 33% efficiency. So you're not really getting much advantage by just cramming in more and more layers, particularly since that peak wavelength represents a peak that's pretty wide. As I said, the sun's peak wavelength is in the green range, but emits plenty of light all the way up to the UV range, and more than half of its light is emitted below the edge of the red light spectrum in the infrared range of the spectrum. That math we just did for Carnot's cycle is the absolute maximum efficiency physics allows. Practically speaking, you won't even get that. And you need to do your spacing to optimize the next layer. For instance, if you're using semiconductors to convert photons into electricity, essentially how solar panels work, you want to optimize your waste light to work best with those. And if you've got yourself a substance that is very good for 10 micrometer wavelengths, a peak wavelength of 290 Kelvin or 62 degrees Fahrenheit, and another that works well at 15 micrometers, which corresponds to 190 Kelvin or negative 118 Fahrenheit, it makes sense to match your layers up to that. We've no idea what sort of specific mechanical or chemical constraints will apply to control that optimization, so we can't really say much about how many layers and their spacing we'd have. And indeed, you don't have to have discrete layers. This works perfectly fine in a swarm format too, more of a fog or cloud around a star than discrete layers. Your fundamental limit is the temperature of the star, and how hot you can make your computers and related equipment run at, for the bottom layer, and for the top layer, the sort of ambient temperature your area of the galaxy or universe has, and how much construction material you have. The whole universe is saturated with photons at about 2.7 Kelvin, which happens to be about the transition point between infrared radiation to microwaves, and why we call that cosmic background radiation as CMR or CMBR, cosmic microwave background radiation. Way back in the day, it was a much higher frequency, shorter wavelength. Back when the universe was younger, about 400,000 years old instead of about 14 billion, the universe was a pretty dense and opaque fog of a place. And quite hot, too. Basically, the entire universe was the temperature of a star's surface, all glowing white hot plasma, But it was cooling down from the universe expanding, and finally reached the point that atoms with nuclei and electron shells could exist, and when they popped up the universe wasn't opaque anymore, and photons could travel long distances without scattering and getting absorbed. Since the nature of the expansion means that no matter where you are around, there will always be photons from that era just showing up, where you can still see that initial wad of photons, and they are everywhere. But they redshift, get weaker, over time as they had to cover more and more space to have arrived by now, and that space was expanding and redshifting them. If you measured that CMB some millions of years ago, it would have been a higher temperature and frequency. Indeed, for a while after this original event, the whole sky would have visibly glowed, and it's only relatively recently it left the infrared range and entered microwaves. One day, far in the future, the cosmic microwave background radiation will become cosmic radio wave background radiation, and the coldest spots in the universe won't be 2.7 Kelvin, but thousands or even millions of a Kelvin. That will be important when we get to the black hole forming video in 3 weeks. Right now, that's your bottom limit though, and in fact it's a bit higher because there is plenty of other ambient light kicking around, especially inside a galaxy with all its stars emitting light and random particles whacking into things that set a slightly higher minimum temperature. This is what I mean about never being able to hide a Dyson sphere when I talk about it in the context of the Fermi paradox. Even ignoring the very obvious gravitational anomaly of a missing solar system, which would be easily seen by any Kardashev II civilization, and the way it would block light from the other side of it, it still emits waste heat. That's how the Matrioshka Brain works, after all. If we didn't have any of that background radiation hitting our Dyson sphere and warming it up, we'd still need to make it very big to get it down to 2.7 Kelvin. Our sun's surface glows at about 6,000 Kelvin. If we wanted it to glow at half that temperature, as I mentioned earlier, we need a shell around it 4 times wider. And if we built a shell around the sun where Earth was at, it would glow at the temperature Earth does, around 300 Kelvin, at Earth's distance of 1 AU, 1 astronomical unit. At 4 AU, it would be about half that temperature, or 150 Kelvin, 75 Kelvin at 16 AU, out near Uranus, and at 64 AU, a bit out past Pluto, it would be more like 40 Kelvin. At that point, all of the background radiation starts actually being significant to the temperature, but if we just ignored that, to get a sphere at about 1/100th Earth's temperature, or at about the background temperature of the universe, you need to have 100 to the 4th power, or 100 million times the surface, which would need a width at the square root of that, or 10,000 times as far away from the sun as Earth is, 10,000 AU in radius, about a sixth of a light year, or 2 light months in radius, and double that for its diameter or width, which incidentally would be about 4 million times wider than the sun, and take up about 16 trillion times the surface area. That's a pretty big object to miss seeing, and again, it won't actually be that temperature since it's also absorbing and re-emitting all that background radiation hitting it from outside. You could never get a Dyson's exterior layer down to that temperature. Sometimes folks suggest to me that it might be close enough to that temperature to hide, since there are warm and cold spots in the CMB. But I think most folks don't realize that those cold spots, for instance, the big giant ones that bother cosmologists, being colder than 2.7 Kelvin, everything is supposed to be, are actually a lot less than 1,000th of a Kelvin off from the norm of 2.7 Kelvin, 70 millionths of a Kelvin normally. If you had a variation of even 1,000th of a Kelvin, it would show up to us, now, with all modern tech, like if someone took a big white canvas with slightly off-white shades and maybe a few very light gray spots, then put a big black mark on it. To dampen that down so a Dyson might pass for a warm spot, it would need to be so large you'd end up needing to move other stars out of the way to avoid including them, which, as I mentioned a couple episodes back, is not exactly a covert and subtle thing either. But let's stick with that 10,000 AU radius for a moment, the one with 100 million times the surface area of the classic Dyson sphere. I've mentioned before how you don't need much more than a large asteroid or maybe a very small planet to build a very basic Dyson swarm, if it's just very thin, but something with 100 million times the surface area would need 100 million times the building material, which would require hundreds of stars worth of material. And it's kind of hard to imagine why that would be considered a practical idea, especially considering that fusing all that construction material up from hydrogen would release a few hundred times more energy than the sun would emit over its whole life. Again, not a very subtle or covert thing to do. So we can't really use that top reservoir of 2.7 Kelvin for computation, nor to hide a Dyson. It's impossible, not to mention insanely impractical, to try to come close to it. You can make a pretty good case for building your swarm all the way out to Pluto, since you'd only need a couple thousand times the normal Dyson mass, not 100 million, and since at those temperatures you can still basically disregard background radiation. But past that, you begin getting seriously diminishing returns. That dynamic changes a lot if we're using black holes instead of suns as our engines, and if the CMB has dropped down to a lower temperature. But we'll look at that more in the black hole farming video in a few weeks. Now, I already mentioned the Carnot limit on efficiency of heat engines, and a Dyson sphere is definitely one of those. But in the past I've also mentioned something called the Landauer limit, which puts the absolute maximum on how much computation you can get out of a processor for a given amount of energy at a given temperature. Our computers nowadays don't run anywhere near that limit. It's the sort of thing that lets you run millions of supercomputers or whole brain emulations off the power of a light bulb. But it also needs to be considered for a Matrioshka brain, and I was a little disappointed nobody seems to have done an analysis on that. See, the star's luminosity, its power output, puts a maximum on how much power each layer has to do calculations with. And Carnot tells us what percentage of that we can actually convert to do work with, in this case calculations. And again, if you're going in powers of 4 for your distance, having the temp at each step, that would be 50%. But Landauer tells us how many calculations we can do with that power, or how much power each calculation takes minimum. And that's linear to temperature, so your inner and outer layers do less computing than your outer layers. If they are each running at that limit, each successive layer at half the temperature is actually doing twice as much work in terms of calculations. It's not really smarter though, since it may be doing twice the thinking, but is spreading that out over 16 times the area. So smarter but slower perhaps. Signal lag is a pretty big deal for such things. But only if they are singular intelligence. We usually envision it that way, that's why it's a Matrioshka Brain, but it hardly needs to be singular. You can run tons of smaller minds, human ones or much larger, and not really have that lag issue. I think in the transhumanism or simulation hypothesis video, I said based on current approximations of computing power needed to run a human mind, you could do it with a solar panel about the size of a postage stamp. But let's be a bit more formal about this, and in the context of the nested layer Matrioshka Brain. Let's just say for the moment that everything is running perfectly, so we only need to consider Carnot and Landauer limits. Now, it's fairly simple to recognize that only your last layer really matters. Each one above it would do half the processing, and 1 plus half plus a quarter plus an eighth and so on adds up to 2, which would negate that 50% efficiency from the Carnot limit. And that's almost regardless of what your star's temperature is, that when contrasted against the CMB, you end up with near 100% efficiency. The real power comes from how cold your last layer is, not how hot your star is, though this only works this way if you can actually compute down at the Landauer limit. Anyway, you can calculate for each discrete layer and add them up, but it will always roughly approximate the last layer running at just under 100% efficiency and calculating at that temperature, and the whole thing works out to be about 10 to the 49th hertz of total processing, which is about 40 orders of magnitude, 10,000 trillion times more processing power than whatever device you're probably watching this on, and 34 orders of magnitude more than our current best guess to simulate a human mind. So hypothetically, your Matrioshka brain could run 10 to the 34th or 10 billion trillion emulations of people simultaneously and in real time. That's a lot more than the about 10 billion people we have on Earth, or the about 10 billion we'd expect a classic Dyson sphere could hold. Though in the upcoming Arcology and Euclid Monopolis videos, we'll see those are a couple orders of magnitude shy of plausible comfortable maximums. But that's still a couple orders of magnitude, not a couple dozen. And if you scale this up to be galaxy encompassing, having one around each star, you could add 10 or 11 more orders of magnitude on to come out at around 10 to the 44th or 45th power. And none of these folks would really need to worry about lag time, for their own thoughts at least. Even if they are running a lot faster than a normal human mind, or a lot bigger. The power plant for a mind at the hot bottom layer is smaller than a pencil dot. And even out on the outermost layer, we'd still be talking about a normal-sized modern solar panel. Now, it's pretty obvious what you do with all that processing power if you're emulating people, And I generally don't think of it as an emulation. A mind is a mind whether it's running on brain cells, computer chips, or a million monkeys or ants, each replicating the action of a brain cell, like we discussed in the transhumanism video. But whichever, you use that processing power to run people. On the other hand, if we're talking about one big megamind, or problem-solving tool, it's kinda hard to imagine what you do with all that computing power. Especially an upgun version of this where you need to calculate really quickly and build it around a giant star with a much higher surface temperature and tens of thousands of times more power, like Spica, or even bigger ones potentially millions of times brighter than our sun, or around a neutron star, for when you need to solve the secrets of the universe or the gajillionth digit of pi on a tight schedule, I suppose. And the answer to what you do with that much processing power is, I have no damned idea. I generally tend to think things like how to break the speed of light, or laws of thermodynamics, or jumping into other universes is either flat out impossible, no matter how much brains you throw at it, or something you could probably solve with a lot less than a god mind, which is the only meaningful way to even look at a Matrioshka brain as a singular intelligence. I have no idea what they spend their time thinking about, but when you've got the processing power to simulate trillions of words simultaneously, through their whole history, in an eye blink, without working up a sweat, it throws some strange light on concepts like the simulation hypothesis. We talked about superintelligence a couple weeks back, and beyond defining it generally, we couldn't make much headway, and I've never seen a fictional example in any of the tons of sci-fi novels and short stories I've read that have managed to represent anything significantly smaller than a human in a way that felt believable to me, let alone something of this sort of Leviathan capacity. Okay, so that was Matrioshka Brains, which closes out our look at Dyson spheres too, and sort of brings us to the end of the megastructural series in terms of scale. We can go beyond this in terms of scale to look at galaxy-spanning structures, or even ones using multiple galaxies, but it really is just an increase in scale, not concept. We can and will go beyond these in terms of time, to look at how objects like these might continue to exist in slightly different ways when you can't use stars anymore, when we look at black hole forming in 3 weeks. But before that, we'll be heading way back down in scale to look at alcologies, giant structures that are a sort of mix of skyscraper and space station that we can build here on Earth, and following up the next week with an extension of that idea to look at Eucomenopolises, planet-spanning cities. And we'll have some fun poking holes in some of the misconceptions around these, especially the notion that they are sterile, dystopian hive cities of concrete. Alcologies and Eucomenopolises are too connected for me not to treat them as a single subject, even though we'll be breaking them into 2 videos, so we'll be going back to back, especially because there's a lot of material to cover, since a proper Eucomenopolis has to also take into account the sorts of swarms of space stations, satellites, and habitats around the planet that would be every bit as much a part of that world city as ports, railroad yards, and suburbs are to major metropolitan areas now. So those are our topics for the next 3 weeks. Alcologies, followed by Eucomenopolises, followed by black hole farming. If you want alerts when those and other videos come out, make sure to subscribe to the channel. If you enjoyed the video, please like it and share it with others. And if you'd like to support the channel, you can visit us on Patreon. Questions and comments are welcome, and as always, thanks for watching, we'll see you next week, and have a great day.